let's dive into one of the most powerful and honestly most essential data structures in all of Java, the map interface. If you've ever found yourself needing to connect two pieces of data, like a username to a user ID, or maybe a product to its price, then you are in exactly the right place. So let's start with a really common programming problem. You've got data that's naturally linked together, right? A student and their grade, a city and its zip code. The question is, how do you store that information so that the link between them isn't just in your head, but actually baked into the code? I mean, sure, you could try to use something simple, like a list or a set, but they just hold a bunch of items in a line. They have no idea that this specific student goes with that specific grade. You end up with a confusing mess, and that's where the Java map comes in to save the day. And this right here shows the problem perfectly. Look at the left. With two separate lists, you're just hoping that the student at index 5 matches the mark at index 5. It's messy, it's easy to break. But now look at the right. The map creates a direct, unbreakable link between each student and their mark. It's clean, it makes sense, and it's exactly what we need. Okay, so what is a map officially? Well, it's an object that maps keys to values. And here's the most important rule of the entire game. The keys must be unique. You can't have two students named John in your map. Each unique key points to one and only one value. You know, the best way to think about this is like a real-world dictionary. You look up a unique word, that's your key, to find its definition. That's your value. It's a direct lookup. This super simple concept is what makes maps so incredibly fast and useful. All right, let's see some code. To add data, you just use the put method. So we put John with a score of 85, and we put Alice with 90. Simple enough. But look at that third line. We're putting John in again. Does it cause an error? Nope, because the key is unique, it just updates John's value. His score is now 95. This is that unique key rule in action. So we've put data into our map. How do we get it back out? It's just as easy. You use the get method and you give it the key. Map.getAlice immediately gives us back her score, 90. And notice, we're not using a number like an index, we're using the key itself. This makes the code way more intuitive to read. Actually, this is a great time to pause. Why don't you try creating a quick map of your own and retrieving a value? Okay, we've got the basics, but here's the thing. Map is an interface. It's a blueprint. That means there are different types of maps you can actually use. So how do you know which one is the right choice? Right? Because when you're building a real application, things like speed matter. Is one map better for reading? Is another better for writing? And believe it or not, does one type of map actually use less electricity than another? This table gives us a really nice breakdown. Looking up data is super fast in both types, basically instant, what we call O1 time. But look at modification. For a regular mutable map like a hash map, changing it is also super fast. For an immutable map though, you have to create a whole new copy, which gets way slower as your map gets bigger. And what about that energy question? Well, studies have actually profiled this, and we have a clear winner. For most everyday tasks, HashMap is the king. It's the most energy-efficient choice. And at the other end of the spectrum, you've got TreeMap, which, while great for keeping keys sorted, is also the most power-hungry. So HashMap is looking like our go-to choice, but with great power comes, well, a few traps you really need to be aware of. Let's dig into some of these advanced real-world issues. Oh man, this is a classic bug that gets everyone at some point. If you're looping through a normal hash map and anything else tries to change it at the same time, even your own code inside the loop, your program is going to crash. Hard. That's because standard hash maps are just not built for that kind of simultaneous action. They aren't thread safe. So what's the fix? Well, Java gives us ConcurrentHashMap. As you can see, it's built from the ground up to handle multiple operations at once without blowing up. The takeaway is simple. If more than one thread is going to touch your map, don't use HashMap, use ConcurrentHashMap. Here's another subtle trap you need to watch out for: the null value. A regular hash map is pretty chill. It'll let you have one null key and as many null values as you want. But ConcurrentHashMap and those immutable maps from map.of are much stricter. If you try to give them a null key or value, they'll throw an exception right away. You know, there's another great way to guarantee safety, and that's to make the map unchangeable or immutable. If you create a map that can't be modified after you create it, then all those concurrency problems just disappear. Java's map.of is perfect for this. It creates a locked-down, read-only map that is totally thread-safe by its very nature.
All right, pro tip. When you need to loop through everything inside your map, this is the best way to do it. You grab the entry set, which gives you a collection of the key value pairs. Then you can loop over that and get both the key and the value in one go, without having to do a second lookup. It's clean, it's efficient, it's the way to go.
And of course, put and get are just the beginning. Maps have a whole toolbox of other methods. You can remove entries, you can check if a key contains key, you can get the size, or you can just grab a list of all the key set or all the values. It's a really complete toolkit. So let's wrap this up. What's the big idea? A map is all about storing key value pairs where the keys are unique. It's an unbelievably useful tool for giving your data structure, for making those relationships explicit, and for retrieving information using a meaningful key instead of just a random number. We've seen that HashMap is usually the best choice. It's fast, it's energy efficient. But how does it do that? How could it possibly find one item out of a million almost instantly? What is the secret sauce that gives it that incredible performance? Well, that's exactly what we're going to break down in our next explainer. See you there.